last time we worked through a lot of things is in regards to Ampere's law, and the goal was to get to a point where we could finally honestly answer your question,
Yes.
which was initially about a solenoid
Mm-hmm.
and using Ampere's law to prove the field generated by the solenoid on the inside
Mm-hmm.
and the zero field on the outside. And that question made me realize that, oh my goodness, textbooks are, I don't want to say lying, but they are certainly omitting crucial information for ease of teaching and education, right? So there's
Mm-hmm.
a lot of hand waving that goes on when we talk about solenoids. And that hand waving basically forced me to prove Ampere's law, the general case, for myself so I could honestly answer that question. Um, the straight wire case, everybody's done it. Everybody who's taken the course knows how to do it. It's a very straightforward case. So we spent a little bit of time talking about that in the last part. And then we worked our way to the general case where you could have any kind of a curvy current wire and asking if Ampere's law works with those. So
Mm-hmm.
I figured we just do, like a brief recap.
All right.
So I know you had mentioned that you might go back and kind of scan through the video. I would understand if you didn't. Would you say that happened or no?
I was not able to do that.
No worries. No worries at all. Because honestly, I kind of made this because I feel like a recap is nice to kind of set the stage.
Okay,
So,
cool.
we've got this amp loop, which is just a figment of our imagination. It's some loop that we're going to walk on.
Mm-hmm.
Um, and then we're going to, every step along that loop, we're going to ask, how much is the magnetic field in alignment or disalignment with me?
Mm-hmm.
And every step, we find that using a dot product between the step you're taking and the field at that specific point. And we call that a contribution to circulation. We take every step along that loop and do a full loop and ask how much does every point have a field contributing to our walk.
Mm-hmm.
And when we do that in a full loop, as I have written right here, we get a value called the circulation, which really,
Yes.
if it's positive circulation, the field is really in alignment with the path you're taking. Negative means it was more, on average, disaligned with the direction you're trying to walk. Um, and we realized that with a long straight wire, there was kind of an advantage to doing this in polar cylindrical
Mm-hmm.
coordinates because there's a nice cylindrical symmetry there.
Mm-hmm.
And so the idea behind symmetry that we discussed last time is that really when we say symmetry, it's a loaded term, but what we really mean is there should be no way that I can detect where I'm at in this coordinate system. So in
Mm-hmm.
other words, if I'm standing right here at some coordinate r and theta in my cylindrical system, there should be no way for me to tell that as being any different from being at the same radius and some separate angle over
Mm-hmm.
here,
Yes.
right? Like the wire's going to look the same, the current's going to be flowing in the same direction.
Mm-hmm.
Visually and perceptually, there should be no way that I can tell what angle I'm at on this wire.
Yep.
And so we called that like azimuthal symmetry in this case would be, there's no preferred coordinate system for a fixed radius as you walk around. And because of that, there is certainly no way that the B field could be different on that constant radius loop. Otherwise, we would cheat nature and we
Mm-hmm.
would be able to detect where we are in a
Right.
truly undetectable system.
Mm-hmm.
So that's why the azimuthal component or theta was undetectable in their symmetry there. Then we had the Z, right? We've got this infinite straight wire. So if I walk over here and I walk over here, I look either direction and visually the wire looks exactly the same,
Mm-hmm.
right? The further I go this way, well, the wire goes on forever. The further I go that way, the wire
Mm-hmm.
goes on forever. So there's no preferred Z coordinate. But there was one coordinate that was preferred in this system, and that's the radial coordinate,
Yep.
because you can absolutely tell whether you're touching the wire or not.
Mm-hmm.
And as you walk away from the wire, perspective wise, it will appear to thin up.
Mm-hmm.
So we were able to detect where we are in the radial direction. And so because of that, we decided that the B field had better only be dependent on the radius in order to prevent us from detecting things that we really shouldn't be able to.
Yep.
So we knew B was going to be only dependent on radius, not on Z or theta. And then empirically, right, we talked about when people were studying magnetic fields, we had compasses for quite a while at the time. And then when they started getting current carrying wires, somebody passed a compass near the wire, and whoa, the compass lined up
Mm-hmm.
in such a way that no matter where you move the compass, that the alignment of the compass was always in this like azimuthal direction. And
Yep.
so empirically, they found out that the magnetic field caused by a long current carrying wire is in the theta direction. And then using symmetry, you can kind of say, well, we know it can only depend on R. Do you remember my argument as to why it depends on 1 over R instead of, say, 1 over R squared or R cubed?
Um, I don't really. Well, Well, let me think about it for a second,
Yeah.
though. So if it's 1 over r, the further you go out, the smaller the B field would be.
Yep.
And so, but why wouldn't it be? Why wouldn't it be 1 over r squared?
Yeah. So yeah, there's that thought of, well, hey, the further we get away, well, the field should get weaker.
Yeah.
We're further away from the magnetic field source. Um, and we kind of know that the magnetic field source is really the current,
hmm
right? That's what's driving the B field.
hmm
As far as I can tell, wherever there's a current, there's a B field.
Yes.
Um, with the symmetry we have here, of what significance is 2 pi r,
Oh, is that the perimeter, or is that the
right?
right, like the circumference of
Yes,
the loop?
exactly. So that represents the circumference that has the wire concentric to
Yeah.
that circle. And so the idea we had was, hey, here's this infinite wire, and it's spreading its influence across the surface area of an infinitely long cylinder. So in other
Okay.
words, nature has no preferred direction for magnetic influence, so it's shooting magnetic influence radially outwards. So it's got to be spread over the surface area of a cylinder.
Yeah, yeah, absolutely.
And why the 2 pi r came in, well, we said, okay, so the magnetic influence is really, well, longer wire should give you a stronger field. So
hmm
he said the magnetic influence should really be some value of current. Then we've just got our arbitrary constant, right? Arbitrary constant current matters, right? If you pump up the current in the wire, the field should strengthen.
hmm
And longer wire should also strengthen the field because that's more point sources of current.
Sure.
So this is the magnetic influence, is what I would call it. And then we have to spread that influence across the cylindrical shell. And a cylindrical shell has area of 2 pi r times L, right? The
hmm
circumference kind of extruded out
So this is kind of like saying the magnetic influence per like
per unit area.
yeah,
Yes.
exactly, because
And
it's an
yes,
area.
exactly. And actually, that's the same with the electric field strength too. The
hmm
electric field strength is more of a measure of how many field lines per unit area. So,
Right.
funny enough, the electric field strength is more of an electric field line density measure. And the magnetic field strength is also kind of a magnetic field line density
That's
measure.
pretty cool.
Yeah. So those lengths cancel out. And
Yep.
so, even though, yes, they found this empirically to be the magnetic strength as you go out radially, there is like a good kind of logical philosophical argument for why that would be the case, right? We've got influence spreading over a cylinder's surface area.
hmm
So at that point, we kind of dug a little bit more into circulation. And with circulation, we found that it actually only depends on the change in angle, theta, delta theta, right?
Yep.
So for some reason, the radius didn't end up mattering. And that's what we'll show on the next slide real quick. So if you walk in the, say, the r hat or the z hat direction, that will not affect circulation. And the reason why is because the field is always in the theta hat direction. And no matter where you're at in space, r hat, z hat, and theta hat are perpendicular. They're all orthogonal to each other. So if the magnetic field is only pointed in the theta hat direction, then stepping in the r hat direction or the z hat direction, the field will always be perpendicular to you during those steps.
hmm
So the field, there's no circulation contribution there. It's zero.
It's because of the
So
dot product. You can think of that too.
precisely because of the dot product, right? And
Yeah.
actually, I think, yeah, maybe you're spot on. I think I actually missed that in the last one, which was that in polar cylindrical coordinates, when you take a step dp
hmm
along your path, that step dp can be comprised of a small step in the r direction
Yep.
or a small angular rotation in
hmm
the theta direction, right? But we know that angular rotation isn't the same as a displacement.
hmm Yes.
So, you might see, oh, these two things are 30 degrees separated, and it could be a dog and a child a couple of feet away from you that are 30
hmm
degrees separated, or it could be, the Sears Tower and some lake. I can't remember what lake Chicago is next to. What is it,
Oh
Lake
God,
Michigan? I don't know.
I don't know.
Anyways, we'll say it could be two landmarks far in the distance.
Sure.
The point is that the true displacement in the angular direction has to include how far away those objects are, as well as the angle, to tell you the displacement between those two objects. So
Sure.
we came to that in the last session, that the displacement for a small angle is r times d theta.
hmm
If d theta happened to be a full 2 pi or a full circle, then we would just get 2 pi r.
hmm
And that's the circumference, and we know
There you
that
go.
that's the case, right, for a
Yep.
circle. So. And then we could take a small step in the z direction, which is a true displacement. So dz, z hat. So that's important. to understand what happens next.
Yep.
So I've got kind of two loop cases here. For loop one, the amp path does not have the current wire penetrating it, right? There's no current threading through it. And what we notice when we go ahead and take tangent lines from the current wire's perspective is that there's a tangent point A and a tangent point B. And because the magnetic field loops around the current wire in respect to the right-hand rule, as we're walking this loop, we walk from A to B, and the field is helping us. So that's positive circulation contribution. But then when we turn around and finish the walk from B to A, we're being opposed by that field. So in order to find the total circulation in the loop, we take the circulation as we walk from A to B, and we add the circulation as then we walk from B to A. And boy, I feel like I skipped through it again. I'm jumping the gun on these slides. So when we did the dot product, like you mentioned earlier, to find the circulation, we knew what the magnetic field was. It was mu sub naught I over 2 pi r theta hat. We dotted it with our small displacement on the amp loop path dp. And because it's a dot product, B field didn't have an R, didn't have a Z, right? So all that was left was mu naught I over 2 pi r times R d theta. And this is the beauty of Ampere's law, is those R's canceled out. And we got mu naught I over 2 pi. Then just sum up all the little changes in angle for each dp. And that just gives you the total angular displacement of the path. So this was our formula for circulation along a path. It's just mu naught times the current in the wire, divide 2 pi, times however much of an angle you pass through.
Beautiful.
Awesome.
Beautiful.
So we get back to here, and using that, like we said, total circulation, this circulation plus this circulation. To find the circulation as we walk from A to B this way, we know it's a positive circulation because the field is helping. So positive mu naught I over 2 pi, then times delta theta from A to B. So that's this angle right here, the angle as we go from A to B. And then to find the circulation from B to A, we're pretty much doing the same process. We're just walking from B to A, so the field's hindering us. Therefore, we put a negative sign up there. It's going to be negative circulation. Mu naught I over 2 pi times the change in angle as you go from B to A. And what do you know? For a closed loop path, delta theta from A to B is the same value as delta theta from B to A. So for that reason, the case where the current does not thread the loop, we found a circulation was 0. And then for loop 2, when the current did thread our amp path, this time we didn't even have to break it up into 2 chunks, right? Because the entire walk, the field is helping. See the field I've tried to draw in blue lines there is helping the whole way. And so now we just need to know, hey, we did 1 full loop. 1 full loop is an angular displacement of 2 pi. And at that point, we find that the circulation is simply mu naught I. Because when we plug in 2 pi here, cancels the 2 pi there, we get mu naught I. And that was kind of a hint at Ampere's law. But certainly not a proof, right? Like this is a straight wire. It's an infinite straight wire. Like this is certainly not sufficient to say that Ampere's law works with all wires, curved wires, any sort of wire.
Very special case.
Very special case. Lots of symmetry. When path loop encloses current. So note, if you walk the loop n times, so in other words, if I start here and I go, I walked the loop once, I walked the loop twice, now I walked the loop 3 times, then the circulation is going to be the number of times you walk the loop times mu naught times I, because you gain an additional mu naught I of circulation every time you walk the loop. Another way to think about it is if you walk the loop 3 times, what would delta theta be?
6 pi.
6 pi, right?
Yeah.
And 6 pi would cancel out and give you 3 times mu naught I, just like we suspect.
Yeah.
That's if we were walking counterclockwise. If we walk clockwise, then we're actually being hindered by the field. And I use hindered in quotes because the field's not actually hindering you. I'm just talking about it as if it were a flowing stream or river or something.
Sure, I know what you're talking about here.
And then walking clockwise, you simply flip the sign of the circulation, right? So if you walk clockwise 3 times, you're just going to get minus 3 mu naught times I circulation. So that pretty much covers it for the long straight wire. Now we get to talk about what happens when you have, or actually, wait, one more thing here, which is you can't fool nature. So that's what this slide's all about. So if the path is viewed as if the path is viewed as a solid loop, if the path itself, the amp loop path, could be untangled from the current wire without having to cut the amp loop path or the wire, then the circulation is always going to be 0.
I see what you're saying because it's
Yeah,
almost like the current could just walk out of the loop.
exactly. Right, right. I'm thinking about this like those magic tricks where the magician has the two rings and then they can link
Yeah.
them together, they can unlink them. It's impressive because like deep in your mind, that's not possible with two solid rings, right?
Yeah.
So yes, in this case, we have a starting point A, and we could walk from A to B. Hey, the field's helping, helping,
Hmm.
helping, 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 helping. Now we walk to B. Now the field's hindering, 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 back to A. And the delta theta is the same for both. The sign's the different thing.
Hmm.
And so it still ends up canceling us and giving us a circulation of zero.
Yep.
And like you just mentioned, right? How could you untangle the wire in the amp loop? And you said it. The current wire could simply walk out of it, right? It's not linked, it's a maze. And mazes aren't always
Hmm.
easy to get through. And sometimes they can confuse our minds, but there's always a way out of that maze in
Yep.
this case. So nature can tell how many true loops you've completed and how many you've undone. There's no tricking it. Then, in order to get into the curvy wire, we had to start talking about the Biot-Savart current element, which Biot and Savart were two gentlemen, I believe, in the 1820s. They empirically found that short little stretches of wire tend to create a specific kind of magnetic field. So what they did find is, hey, even if this isn't a really long wire, we got like a short little bit of wire, really stubby bit of current wire,
Hmm.
that the magnetic field still curls azimuthally around that wire. So just like with the long straight wire, it's only that theta hat component
Hmm.
um, that exists. There's no z hat component. There's no r hat component to that field. It's all curling. What they also found was that the magnetic field was proportional to sine of phi divided by r squared. So phi, if you were to point an arrow in the direction of the current of the wire, call that arrow a small bit of wire, dw, then pick a point of interest where you want to calculate the field.
Hmm.
If you draw a radius from the wire to that point, then phi would be the angle between the current and that point.
Hmm.
And then the radius, of course, would just be the total distance, straight line distance between the Biot-Savart current element and the point that you're trying to calculate the B field at. So in this case, the field is dropping off as 1 over r squared again. Remember, with the long straight wire, if it fell off as 1 over r, we could justify that because it was spreading its influence over a cylindrical shell. Now the field drops off with 1 over r squared, and it's not as easy to justify as a point charge, right? With a point charge with electric field, we just say, oh, well, the field's the same everywhere on a spherical surface,
Hmm.
same absolute magnitude of the field on a spherical surface. And a spherical surface area is what?
4 pi r squared.
4 pi r squared. So now you're taking the charge's influence, the number of field lines in essence, and dividing it by the surface area it's spread over, the
Hmm.
4 pi r squared. And that will tell you the field line density per unit area, which is the same thing as the electric field. Um, so the field still drops off with the Biot-Savart case as 1 over r squared. And the reason is because if you find, let me just say, if we wanted to find an exact surface of equal field strength. So what I'm saying is, okay, we've got a dB contribution here is given by Biot and Savart. I would like to find all the points in space that have that exact same magnetic field strength. And so to do that, what you do is you take dB, or the magnetic field contribution by this little chunk, and you set it equal to a constant. And so in this case, right, Biot and Savart said sine phi over r squared. That's what they found empirically. And you set that equal to a constant. And when you solve that equation, you get a polar equation that says r of phi, the radius is determined by the angle phi, to have equal field strengths is equal to some constant times the square root of sine of phi. And when you graph that out on Desmos, like I've done over here, this is the shape that you get.
Okay.
So it almost looks like a cross section of an apple.
Hmm.
It's not quite a toroid, but it's pretty close to that. So as it turns out, this kind of a shape, and you could prove this for yourself, is you could do a solid of revolution
Hmm.
to figure out the surface area of this shape. And the surface area of this shape does have a dependence on r squared.
Okay.
So unlike the cylindrical shell, which surface area depends on r, this particular shape depends on r squared.
Got it.
So we're taking the Biot-Savart element influence, and we're in essence spreading it over this weird sort of donut shape. I've got a 3D representation over
Okay.
here. So that's why Biot-Savart element actually drops off as 1 over r squared. But what
It's
do we
very
do?
close.
Okay, so we oh, go ahead.
I was gonna say that is very close to a toroid looking thing.
Very close. Not quite because it's not a full circle. It's got like kind of two different
Right.
curvatures there,
Hmm.
but it's close. So now that we empirically have, oh, hey, a small hunk of wire with current is contributing this much of a field, we could start talking about figuring out what the total magnetic field is at a single point in space caused by an entire closed loop wire.
Awesome.
And that's where we got last time. So to find the magnetic field caused by full wire loop W. So this is the wire W. At a single point in space, which I'm labeling P, coordinates x0, y0, z0, you have to sum all of the Biot-Savart contributions, right?
Yes. Yes, you
So in
do.
other words, this little dW over here contributes a little tiny bit of magnetic field at our point of interest dB.
Mhm.
Then we have to take a step, find the contribution from this dW, take a step, find a contribution from this dW, and so on. And once you've completed that process around the entire current carrying wire loop, you will have a total magnetic field for a single point in space, x0, y0, z0. And to do so, it looks a little something like this. You just integrate the Biot-Savart element across the entire closed loop wire. And in this case, the arrow that points from our coordinate center to the point of interest, where we want to find the magnetic field at, we call that R naught.
Mhm.
And then the vector that points from our coordinate center to a single point on the wire, we call that W.
Okay.
And we parameterize W with a parameter T because actually any curve in three-dimensional space requires parameterization. So you can think of W vector as sweeping out the entire wire loop with the tip of its vector. And it has subfunctions like, oh, what's the X component of the wire in parameter T? What's the Y position? What's the Z position? But the point P that we're interested in is fixed. It's a fixed point that we've picked. And you could probably kind of see the relationship between the vector W and R naught and the vector that shows the distance between the point of interest and the current source that's creating the B field there is
Mhm.
given by W plus the radius or the distance that you plug into Biot-Savart equals the point of interest position. So if you want to know the total radius between the source and the cause and the effect, you could say, right?
Yep.
The thing creating the field, the place where you're measuring the field, it's simply equal to R naught minus W vector. And this would be true no matter what point you're at. If we were interested in this dW, you've got your W vector. That separation vector is still R sub naught minus W.
Gotcha.
So that works all the way around. So we plug that into our Biot-Savart thing. We do another thing as well because Biot-Savart has the wire element crossed with the radius hat direction vector. Instead, we know that R hat is equal to R divided by magnitude of R. So we simply plug that in, and we know that R is this. So we're taking dW cross this difference, and then dividing it by the separation distance cubed, because the unit vector includes that extra magnitude in the denominator. So we could write it like this. You could write a code. You could write a program to do this numerically. Maybe for some wire parameterizations, there's a analytical way to take the integral and solve. But the idea is the same. You just take a small step dW, figure out what that point's contributing to the field, and then continue on until you're through the whole loop.
Cool.
So that was one of the sets up to our problem. Then we had to talk about, because with circulation and an Ampèrian loop, we're not just dealing with one loop and a point. We're dealing with a wire loop that creates a field, and then an amp loop that we need to know the field value for at every point on the loop.
Yeah.
So magnetic circulation was given by this formula, where P is some closed loop path. We call it an Ampèrian loop. B is the magnetic field caused by the curvy current wire W. But Biot-Savart requires integrating the entire wire to find a single B value at some random point P on the amp path.
Mm-hmm. Okay.
So you pick any point you want to start on the amp path. Maybe it's this point. You integrate the whole wire to figure out what the B field is at that point. Then you dot it with your little displacement along the path dP to figure out how much is that B in alignment with my path.
Sure.
Then once you take that step, we have to integrate the whole wire again to calculate the B field for the next step. Then we dot it, we take that step. Then we have to integrate the whole wire again to find the B field at the next spot. Then we dot it with dp and take that step. And we do that all the way around the loop until we get to the end of the amp loop. And at that point, right, if the amp loop is comprised of infinitely many little dWs or dPs, it's comprised of infinitely many little dPs. And for each dP, you must integrate infinitely many dWs going across the wire every time. Then we're already at infinity times infinity level of complexity in this problem.
You can see how this is. You can see how this takes a while to figure out.
It's brutal. Savart requires integrating the entire wire to find B at a single point P. Then once B is known, we dot it with the step on the amp path dP to find the small circulation contribution. Repeat steps A and B as we walk the entire amp loop. Sum up all those circulation contributions, and bam, you've calculated circulation over the amp loop. So a couple of important takeaways here is, once again, the wire is a parametric curve of this form. We'll parameterize it with some parameter t that does not represent time. It's just some parameter. Where if we run t from some initial value to some final value, that will take us around the entire loop once. So it sweeps out the entire wire loop as we go from t initial to t final. Now, because we have the amp loop, let's parameterize that in S. And so in the same way, p vector as a function of S, it just runs between some initial S and some final S, and it will sweep out the amp loop like so if you go between S initial and S final. So at this point, to calculate the circulation, it looks easy up here, but then we realize, oh, we need to do a wire loop integral for every B value we need. So all of a sudden, this right here, this B, turns into this thing. So that's the B field at some point on the amp loop. Once we have that total B field at that one point on the amp loop, we dot it with dP like we've discussed, and then we take a step and we do it again. And so this outer integral then adds up all of the circulation contributions from every point on the amp loop, caused by magnetic fields from every point on the wire. So that's the total circulation about the amp loop caused by the wire. And the way I describe this integral, because I had never seen anything quite like it, or at least never understood, but this is basically math's version of a nested for loop.
Oh.
Right? So most double integrals we've worked with in Calc 3 represent surfaces, or like two different axes, something like that. But this double integral is truly complete this subtask in entirety, then do this higher order task, then complete this subtask again, then do this higher order task, right? And so that's really what it is. That's a type of nested for loop double integral.
I see what you're talking about.
Yeah. So a lot of what we spent doing last week was taking this beast, or not last week, but last session, was taking this beast of an integral and figuring out how to simplify it to where we even had the hopes of understanding it. Because at this point, we have infinitely many integrations within infinitely many, right? So it's like an infinite sum within an infinite sum.
Yeah.
And not only are there two infinite sums, but we're trying to prove Ampe's law for any WT and any P of S. So for any path you pick, for any current wire you have. And before, I think I said that makes it infinite times infinitely complex. But if you consider that there's infinitely many paths to take and infinitely many wires you could have, it's really probably more like infinity to the fourth power, right? It's like, this is ridiculous. It has no business being solved. So it becomes, we had a couple of steps to make it look nicer. Like we use linearity of the dot product and integration, right? So, whenever we're in calculus, we're like, oh, what can I do with this integral? Well, I could pull out the constants. Okay, so integration's linear, so you can pull out the constants. So we pull out the constants. And then we also discussed that the dot product was a linear operation. So basically, instead of adding up all the B field contributions for some point on the amp loop, and then dotting that summation with dP, we could actually distribute the dP to each of the little Biot-Savart contributions for the B field at that point in space. That was valid. So using that, we were able to take the dP from something that was a part of this process and actually integrate it with this sub-process.
Yes.
Then after that, we used a triple scalar product identity, which allowed us to write the dot and cross products in the numerator in a little bit different of an order. Because the triple scalar product, that's whenever you have a cross B dot C vector, those represent the signed volume of a parallelepiped, right? So weird kind of three-dimensional extension of a parallelogram. And as it turns out, there are 3 vector triple scalar products that build the exact same parallelepiped. So, if I draw 3 vectors, say A is here, B is there. I don't know why I put a unit vector hat on there. A is there, B is there, C is here. Then the parallelepiped that this thing encloses looks something like this. So there's our parallelepiped. You can find it by taking A cross B dot C, or you could find it taking B cross C dot A, or you could find it taking C cross A dot B. So just using your right hand rule to make sure that it's the positive volume, because if you take a dot product with 2 vectors that are in opposite directions, you'll get a negative.
Right.
So there's actually 6 of these that share the same magnitude or absolute value, but only 3 ways to build it that give the same positive volume. So it's a brief overview of what we did there. And the reason kind of why we did that was because before we were taking a cross product between an infinitesimal and a non-infinitesimal. This is our radius, our separation vector, and then dotting it with an infinitesimal. And there's just this thought that, maybe it'd be easier to handle if the cross product was between 2 infinitesimals. So this allowed us to take the dot dp and move it to the front. So dp cross dw dot the separation vector between that point on the wire and that point on the amp path, and then divide by the cube of the magnitude, or the cube of the magnitude of the separation. So, and I'll just say it for anybody watching the video, if you want more details on those steps, refer to part 1. And then another note here, because as we discussed, p vector as a function of s minus w vector as a function of t is really just a way to write the separation vector between that point on the wire that's causing a magnetic field contribution on the amp loop path and the amp loop path itself. And likewise, if we take the separation vector between the path and the wire and divide it by the magnitude, that gives us the unit vector, right? A vector of length 1 that simply points from the wire to that point on the path with length 1 and it's dimensionless. So using these 2 things, we can rewrite our circulation double for loop integral as this. We could write it as mu naught I divided by 4 pi, closed loop integral of the path, closed loop integral of the wire, dp cross dw dot r hat divided by magnitude of r squared.
That looks a little better.
Looks a little better, still seems impossible. We had one more breakthrough to really get out of the way. And that breakthrough was solid angle. So yeah, most of part 1 was dedicated to showing that the integrand of our circulation integral, which was this is the thing at the heart of the for loop process, actually represented signed solid angle. So then we kind of drew a picture and we said, if you were an eyeball taking a small step on the wire, the current carrying wire, so you take a small step dw, and then you're fixing your eye on a single stretch of the amp loop path. So dp is a single little bit of the amp loop path. You take step dw, and we found that would make that little chunk of the amp loop path appear to sweep over a surface. Like, it's this weird thing about perspective where you'd have to close one eye to really get a feel for this, because with 2 eyes, you get depth perception, right? You can kind of tell how far away things are. But with one eye, there's really no such thing as distance when it comes to field of view. You just have a certain amount of field of view, whether half of it's taken up by the sky and the other half by the ground, or whether the whole thing's taken up by a room and construction material, right? So we decided to start treating this sweeping as if it was happening over a unit sphere. A unit sphere has radius 1. And so as we took that step on the wire, we saw this little chunk of the amp loop path sweep over and create a little bit of signed solid angle, which we called d omega. And d omega, we decided, could be found by taking the perpendicular component of the amp loop path divided by the magnitude of r, because that's how things scale when you get further away from them, right? If you have a pencil here and it's 2 inches, or I'm sorry, if you have a pencil here and it looks like it's 1 unit tall, and then you move it twice as far away, it will appear to be 1 unit tall. Double the distance, half the size. Triple the distance, 1/3 the size, right? So when you're looking at what I call apparent size or apparent length is really just an angle. Like we talked about before, 30 degrees is some apparent length. And I can have 2 things that appear to be the same length that are absolutely not the same true length just because of my perspective, right? Whenever there's a big eclipse that happened in Spain. I don't know if you've seen those videos, but
Hmm.
I was really jealous that I didn't get to go. But the moon is like what 400 times smaller in diameter than the sun,
Hmm.
but it's also 400 times closer. And so it can take up the same apparent patch of the sky as the sun.
Yep.
And we call that patch of the sky solid angle. So the moon and the sun have the exact same solid angle from our perspective.
They appear the same.
They appear the same, right? That's why I call it apparent size and apparent length.
Yep.
But apparent length is really just angle.
Hmm.
Apparent size is solid angle.
Solid
It's
angle.
the 3D extension of
Gotcha.
angle. So yeah, we were able to directly tack the integrand or the kernel of our integral process
Mm.
to this sweeped out solid angle. It's almost like the DP projection smeared over the surface as we took a step. And that's pretty cool to take such a complicated problem and turn it into something that you can visualize.
Yeah.
So that was a good sign. So we concluded that whatever this nasty double integral was doing, we could reduce it to what the amp loop looks like to an observer walking the wire. What does it look like it's doing? And also, once again, more details go back to part one. We spent a lot more time deriving exactly why this integrand is sweeped out solid angle. All right. Now we're to new stuff, right? All of that was what we did last time. New stuff now. So
Cool.
I kind of want to talk about maybe switching the order of integration to make it a little easier. But first, I want to point out that this circulation integral that we've reduced everything down to, we're going to start calling the integrand of that d little omega.
Okay.
That's the tiny bit of solid angle swept out by a dp vector as you take step dw.
Right.
In the current order of integration, which is integrate the wire every time for every step you take on the path, right? So it's integrate the whole dang wire for every step you take on the path. So in that current order, for every tiny bit of the amp loop dp, we walk the total wire. So we're walking on the wire, the whole wire for a single dp to see how that dp smears across our field of vision.
Mm-hmm.
The unit sphere around the eyeball is our field of vision, right? Then, after fully tracking how that dp smears across our encapsulating unit sphere, then we look at another dp that's adjacent to it, right? We look a little bit slightly over on the amp path and then walk the whole damn wire again and see how that little dp sweeps across our field of vision.
Mm-hmm.
Do the same process, rinse and repeat until you've tracked every dp comprising the amp loop. Note that since all adjacent DPs connect with each other, right? So if I have two DPs here, they're physically connected. This step leads to the next step. Then no matter what your perspective is, those will always touch each other. So if two things are truly touching, it doesn't matter what angle you view them from. They will always appear to be adjacent. So in this case, if you'd imagine walking the wire and looking at a single DP, it's sweeping out this kind of ribbon, right? Sweeping out a ribbon of kind of width, apparent size of dp swept around the unit sphere, whatever crazy curve you're following on the wire path. But its adjacent dp will have a ribbon swept out that will share a boundary with the first ribbon. I wish I had a visual for this, but because the adjacent dps are touching, the ribbons they sweep out will also be touching on one boundary, right?
Mm-hmm.
And so for this reason, we can change the integral to better suit our intuition. Instead of walking the wire for every DP, let's just track all the DPs at once and just walk the wire once.
Okay.
So if you track all the DPs at once, they're all connected, right? Because they form an amp loop. Then really, what are you tracking?
Tracking the entire amp loop, essentially.
Yeah, exactly. It's like, screw this ribbon thing, doing it, a million times.
Yeah.
Let's just do it once for the whole dang loop, right?
Yeah.
So yeah, basically what we're doing now by switching the bounds of the integral, we're basically just projecting the entire amp loop path onto the unit sphere for every step we take. So take a step on the wire, draw the projection of the amp loop path on your unit sphere that you're carrying around with you. Like, okay, it looks this big now. Take a step. Oh, okay, it looks this big now, right? And track how the amp loop projection changes as you walk that full loop on the wire. So all we did there, and I think I'll show it in the next slide here. We switched the order of integration and we kind of talked through why it's valid to do. Since tracking all the DPs at once is the same as tracking the entire amp loop P projection as we walk the wire, we can now switch the order of integration. Instead of walking the whole wire per every DP, Now we look at the whole amp loop per every step on the wire.
Okay.
Totally valid to do.
Yep.
And in this case, we're going to come up with another name. So d omega, little omega, was the small bit of solid angle that was swept out by a little dp,
Mm-hmm.
a little chunk of the amp path. If we figure out what that little bit is for every dp on the amp loop path, then we're going to start calling that d capital omega.
All right.
And d capital omega is the change in solid angle of the entire projection of the loop. So, the loop was this big when it was projected last. I took a step on the wire. Now it's this big. The difference between those will be the change in solid angle as I took that step. And I actually do have a picture for this one, which is good. So if you'd imagine this is your eyeball, this is your unit sphere. Here's the initial projection of your amp loop path on your unit sphere right here. Then you take step dw and you find the new projection. And it's gotten a little bigger because you've gotten a little closer, right? That entire strip, that's the difference between the initial projection, the one that we had over here, and the final projection, that entire strip is d capital omega. And it is, in fact, the sum of all the little d omegas, right? Because if you imagine this, this amp loop is just made up of a bunch of adjacent dp's, then, there might be a d little omega here, a d little omega here, a d little omega here, d little omega there. And when you sum them all up, you get d capital omega.
Sure. Yep.
And you do so by looking at every dp, which is why this integral, the closed loop integral around the amp loop path of the d little omegas, is equal to just d big omega. So now all we have left to do is to walk the wire.
All right.
All we have to do is walk the wire and track how the solid angle that projection takes up on your unit sphere changes. So that's crazy, right? Infinity to the fourth power complexity problem, and it reduces to how does the solid angle of the amp loop projection change as you walk the full wire loop? That's pretty cool.
That is interesting.
I think it was, by the time I got here, I was like, I think we can do it. I think we're out of the woodwork here.
Okay, so give me 1 second to ask a couple questions.
This is a big one.
This might be a dumb question. How come it's still a differential? Why don't you just get a big omega?
Oh, great question. You do.
Okay.
So, and actually, I'm going to hold off on that one because I think that's the next slide.
Okay. All right.
Yes, next slide. How a continuous integral becomes discrete, because this looks very continuous, right? It looks like there could be a lot of different values that could pop out. However, since we always walk a full loop on the wire, we know the projection of the amp loop onto the unit sphere always looks identical at the start as the projection does when we finish walking the wire. Because we're starting and stopping at the same location. And by the fundamental theorem of calculus, if you sum up all the changes in solid angle, the little changes in solid angle driven by taking small steps dw, if you sum them all up for the whole loop, you just get the big change in the solid angle, which is exactly what you were intuiting there. So sum of the little changes in solid angle equals the big change in solid angle. Therefore, this big nasty thing reduced to this, which was the sweeping of a little dp, which then reduced to this, which was the sweeping of the entire projection of the amp loop. And because we're starting where we finished, we just get a big delta omega there that just represents what's the final solid angle that you ended with the projected curve minus what's the initial solid angle.
That's cool.
Now, it's tempting, very tempting at this point to say, well, I'm starting and stopping at the wire on the same spot. So the amp loop projection looks exactly the same. So it should just be 0, right?
That's what I was going to say.
Right. That's very tempting to do. However, we're going to look back at solid angle's 2D cousin, right? Just angle. And you can absolutely end up at the same final position by doing 0 radians of rotation, 2 pi radians of rotation, negative 2 pi radians of rotation, or any 2 pi times n rotation where n is an integer.
Got it. So
we haven't gotten it to 0, but we've gotten it to a multiple of whatever a full solid angle would be.
Yep.
And so with the solid angle of the amp loop projection, the projection could have covered the entire surface of the unit sphere before returning to its initial position. And as per part 1, a full sphere or field of view has 4 pi steradians of solid angle. So that's important to know. Is like, with angle, it's 2 pi radians. With solid angle, we have 4 pi steradians
Mm-hmm.
of solid angle. The reason being because the surface area of a sphere is 4 pi r.
Mm-hmm.
And if you divide out the radial dependence, which is what we do when we care about apparent size instead of true size. I'm
Mm-hmm.
sorry, it's 4 pi r squared. We divide out r squared because apparent size of scale is 1 over r squared. So we divide that out. But the point is that this circulation integral for this 3D monster is starting to look very similar to the circulation for the long straight wire. Remember, the circulation for the long straight wire was mu naught I over 2 pi times the change in angle.
Mm-hmm.
And that change in angle could be 0, 2 pi, 4 pi, minus 2 pi. Well, now we have the circulation for a general curved wire. I'm sorry, the circulation walking a general amp path caused by a general loop of current carrying wire is equal to mu naught I over 4 pi times the change in solid angle.
Mm-hmm.
And like we had discussed, delta omega, or the change in solid angle, because the projection starts and ends at the same spot, because we're walking the wire once, so it's going to look the same when you're done as when you started.
Mm-hmm.
Delta omega has to be an integer multiple of 4 pi, because there's 4 pi steradians in a full field of view. So we plug in that, and what pops out the other side is this nasty circulation integral is now just mu naught I times some integer n.
Aha.
We don't
That's
know what that integer is yet. We haven't really proven it, but it sure looks a lot like Ampere's law.
it
I'm
does.
going to give a little hint, which is, as it turns out, n is called the linking number, and it is determined by how much the current threads the amp loop and how entangled the wire and amp loop are. So you're talking magicians with their little rings, and they stick them together. Like, if you stick rings together once, that's a linking number of 1, right? You
Mm-hmm.
can't get 2 solid rings away from each other with a linking number of 1. But different, more complex curves can have higher linking numbers as well. And as it turns out, and this is where I think a lot of people kind of do a disservice for this proof. Firstly, most people don't even do this proof in an intro textbook. Secondly, in my second or third year E&M course, they did a proof of Ampere's law from Biot Savart, very much like what we're doing here.
Mm-hmm.
But they would just say, oh, now that we have this integral, it's called Gauss's linking integral and blah, blah, blah. And I'm like, okay, but I don't know what that means. Like, I don't understand how this integral spits out an integer. I don't understand what it means. So that's why I really wanted to be able to visualize it. And that's what we've done here is kind of show that as you're walking the wire and looking at the projection of the amp loop, you're going to get some integer multiple of 4 pi because you're starting where you're finishing. All right. Now we really have to go case by case to figure out what that n represents. So what a better place to start than the long straight wire again, right? Because
Sure.
that's like, hey, if we come up with a more extended theorem, a more extended proof, we should always start by making sure it agrees with the simplest case that we know.
Yeah,
So
absolutely.
we've got a long straight wire. We would expect the linking number to be 1. And so let's walk through it. All right. So say you start infinitely far away from an amp loop. What will the projection look like?
It'll look like a small circle.
It'll look like a point, right?
Yeah.
Okay. So you're way off to the left of the screen, and you
Mm-hmm.
start walking, and the amp loop starts as a point. How much solid angle does a point take up in your field of view?
I guess not much in that case.
Basically none, right? Like
Yeah.
an infinitesimal point.
Yeah.
It's not really blocking your view, is it?
Not at all.
All right. So you start with omega initial of 0 steradians.
Sure.
As you start walking and getting closer, the projection gets bigger.
Mm-hmm.
You're adding solid angle. Oh, the projection's even bigger now. And something special happens when you cross through that loop. And that is that the projection now becomes empty, and it's the other side that's full.
Huh.
You kind of see, because once you pass through the loop, over 50% of the solid angle has been covered already.
Yeah.
Right? So now the hole that you're tracking, that projection of the angle, is now a blank spot to be filled in. It's no longer a spot that's growing. And as you walk further away, that blank spot gets smaller and smaller. And most of your unit sphere is filled up with solid angle.
Huh.
And then you continue walking to infinity. What happens to this hole of solid angle that you haven't filled yet? What's that?
It starts getting really small until eventually it's almost like the entire thing is just solid angle.
It's filled up, right? With a full 4 pi of solid angle.
Yeah.
Okay, but part of this proof was I said that the wire loops had to be closed. right? And a long straight wire doesn't feel closed, right? Like,
Hmm.
where's the current coming from? Where's the current going? Like, I don't know. So we're going to use a little trick called closure at infinity.
Okay.
The idea here is that once you get infinitely far away, and now the projection on your unit sphere of the amp loop path is basically a dot, that you walk at infinity in a half circle, right? So you're like, okay, I started at infinity over here. I went to infinity over here. Now I'm ensuring that I always stay infinitely far away from the loop, and I walk back to where I started
Okay.
using this kind of half circle at infinity. So that's
Okay.
how we argue closure in this case. And as you make that walk, the amp loop projection is a dot. So it's not changing the solid angle
Right.
because dots don't change solid angle. It has to have some sort of tangible area.
Hmm.
And by the time you get back to where you started, you have completed a full 4
4
pi,
pi. Hmm.
the radians of solid angle that has covered your surface. So omega final 4 pi steradians, plug it into circulation, and what do you know? You get mu naught I.
Yep.
It's exactly what we expected. And the linking number is 1. I kind of like this too because it makes me realize that now whenever I'm driving down the road and I'm going under a bridge, like if I'm going under an underpass, I start thinking about this and I'm like, depending on how I drive home, I may have gathered 4 pi steradians or I may have undone it, right? Like if I drive back home through the same bridge or underneath the same bridge, then I've undone the solid angle that I added.
Yeah.
But if I go home a different route and don't cross through that bridge again or tunnel or whatever it is,
Uh-huh.
then I've covered myself with 4 pi steradians of that
I see.
object. So that's kind of fun. That when I was really struggling with this concept, I would be driving down the road and like looking for street signs and light posts and like thinking about it. So now case 2, we've got a long straight wire with a near miss. It's a near miss. So we would expect the linking number to be 0 because the wire and the loop are not connected
Yeah.
in a way that we can't, pull them apart. Once again, closure at infinity. So we imagine we start off at infinity on the left. Once again, the amp loop is a point projection. So we start gaining solid angle as we get closer to it. Solid angle growing. Solid angle would be growing here, right?
Hmm.
Then something weird happens, which is the solid angle patch stops growing and it starts getting pancaked.
Okay.
So if I drew an eyeball in this intermediate step, at this point,
It just
it would be like super duper thin, right?
like flat almost.
And notice that this is signed solid angle. So when I project the amp loop onto the unit sphere, I'm making sure to keep the arrows the direction of the amp loop path as well as its size, right?
Hmm.
And something weird happens when it pancakes because this side used to be down and this side used to be up. Then there's a cross through event. And after that cross through event, now this side is down and this side is up.
Interesting.
And man, that really threw me off. I'm like, I don't know what to do with that. Because I know that integrand is signed solid angle. And like, I didn't want to have to look at every DW and every DP and do all the cross products and do the dot products, right? Like,
Hmm.
that seems excessive.
Yeah.
So what I've come up with is this. When a cross through event occurs, you go from having a positive amount of solid angle to a negative. So in other words, over here, we were gaining solid angle. When we have a cross through event, like, I don't know if I were to graph like solid angle as a function of time, the way I'm looking at this is we started with very little.
Hmm.
We gained a lot. Oh, we're pancaking. We're pancaking. We're pancaking. Boom. Now we've got
Okay.
negative solid angle. And so over here, we have a patch of negative solid angle I've represented in red. So at this point, we haven't even accumulated positive solid angle. We're in the hole here. Right?
Yeah.
We're in the red.
Yeah, we're in debt.
But as you walk off to infinity, you start paying off your debt.
Yeah.
Right? And that little patch of negative solid angle gets smaller and smaller until
Goes to 0.
eventually, bam, you're at 0.
Yeah.
You've accumulated 0 solid angle. You've walked far enough away where the amp loop projection is a dot, and you do the half circle at infinity. So no change in solid angle getting home. And so just like we would expect with the linking number, in this case, you have 0 circulation. There was no change in solid angle from initial to final. And so that's the near miss straight wire closure at infinity. So far, our new proof encapsulates the old proof.
Yeah.
But now we want to make it work with the more general curvy stuff. That's why we built it. All right. So this is a little complicated. I'm glad I didn't have to redraw this one today. I was like, I already have a drawing of this one. So, and this one is the one that took me forever to really feel like I understood. So if your eyeball starts here, say this is your initial position, and you project the amp loop path. That's what you get, right?
Okay.
But remember that we're not finding the solid angle, we're finding the change in solid angle, right?
Mm-hmm.
So at this point, should I fill in that hole or not?
Hmm. No.
No, right, because the hole, what's inside the hole, does represent omega initial,
Mm-hmm.
but nothing has changed yet. So I'm going to leave that hole blank.
Okay.
Then as you start walking towards the loop, right, that hole remains. But the solid angle starts growing like this, right?
Okay.
Starts growing out, but there's still a hole in there.
Yep.
Once you get to the center of the loop, you're starting to thread the loop. Your solid angle final is here, your solid angle initial is here,
Mm-hmm.
and the hatched area is what you've got. So you pass through, and I would say at this point, over half the sphere is likely covered. And then you keep walking, right? Now the hole that you're tracking, like most of the sphere is covered in solid angle now, right?
Mm-hmm.
You just have this hole left and you've got this hole left. And somehow this has got to work out, right? To add up to one full sphere. So as you continue to walk, the hole that you're tracking, the current projection, you walk, walk, walk. At this point, this hole represents negative solid angle, right?
Uh-huh.
It represents an absence of solid angle, I would say. Then we get to the cross through event. And this is what's special. During the cross through event, the direction of the loop path P appears to change on your projection,
Okay.
right? We
Yeah.
all know this. Have you ever tried to tighten a screw backwards?
Yeah.
Right? And you're like, oh, shoot, righty, tighty, lefty, shit. You know, like this isn't going to work. So, yes, as you go through this cross through moment, something appears. Extra, extra solid angle.
Got
The
it.
thing was already covered here. Now there's additional coverage.
Okay.
Super cool. And as you start moving around, that additional coverage starts to work its way in
I
to the
see.
final hole you have to fill. And by the time you're done, this eclipses that initial solid angle hole that you needed to.
Okay.
So it's weird. It's like there was one hole, then there's two holes, then that hole had to go from a hole to like an overage of solid angle, and then that comes in and literally like eclipses the hole that you needed it to cover.
That's convenient.
Yeah, you can kind of see why I wanted to do like an animation for this, right?
Yeah.
This would well deserve an animation if I could find the time. Definitely can't do it with PowerPoint animation.
That's interesting.
So yeah, this is really the big case, right? We've got a curved closed wire, we've got some amp loop path, and we've
Yeah.
walked it through, and hey, we threaded it, and the linking number's 1. Do you have any questions about this case?
I think you explained it very well. It's almost
Awesome.
like it moved into the missing hole. That was really
Yeah,
cool.
it's so weird to me because I struggled so hard with this because I'm like, oh, because during the cross through moments, I was still treating it like it was a blank hole
Mm-hmm.
at first. And I'm like, well, that doesn't help me. I've got a blank hole filling in a blank hole. I still need that, right? And that's when I realized there's this heuristic with the cross and dot products that build up the integrand, where the second we go from clockwise to counterclockwise
Mm-hmm.
or counterclockwise to clockwise, it goes from being an absence of solid angle to an overage of solid angle or an overage of solid angle to an absence. And that's why the signature, the signed solid angle is so important. And, whenever we do 3D mathematics, this pops up, right? We do like right hand rule to make sure that we're all on the same page about which direction's a positive torque, right? If
Mm-hmm.
something's going this way, that's a negative torque. If something's going this way, that's a positive torque. But for somebody looking on the other side, it would be exactly the opposite.
Mm-hmm.
Because clockwise and counterclockwise are not coordinate independent. I'm sorry, they're not coordinate independent. You can have two people disagree on them.
Mm-hmm.
So that was the big breakthrough for me. Now the near miss with the actual curved finite wire. So start with an initial position. I did fill in the hole on this one. I shouldn't have. So imagine that's as a blank hole, right?
Okay.
You see, I left it blank
Yep.
over here.
Okay.
And then the patch of other solid angle from the projection is just kind of moving along the
Sure.
surface of the sphere.
Mm-hmm.
But because there's not a cross through moment, there's never a time where there's never a time where the projection becomes a hole instead of a patch. So it just kind of moves along. There is going to be a cross through moment here, though, isn't there?
Mm-hmm.
As you go to the side. So it went from being we're adding solid angle to now we have an absence of solid angle. So I really should have filled this one in red to represent we're in the hole, right?
Okay.
So we're in the hole, we're in the hole, we're in the hole. We go around the circle, we're still in the hole. Then there's a cross through moment again, right here, where we go from clockwise to counterclockwise. projection because the path requires us to pick a direction to go.
Mm-hmm.
So it went from a surplus to a deficit, from a deficit to a surplus. And then that surplus, as we move around, it comes back to settle in right where it started.
Mm-hmm.
Well, if you start with the exact same amount of solid angle you ended with, then you didn't have any change in solid angle as you walk the wire. So that gives us a delta capital omega of 0 and linking number 0.
Okay.
And then once again, I got to talk about you can't fool nature, right? The old in and out. All right, so you start at infinity, right? And you're like, okay, projection's a small dot. It gets bigger, it gets bigger, it gets bigger. Maybe if I can force a pass-through moment, I could fool nature and like lock in my solid angle, right?
Try.
So you try it out, and you do cross through, and at some point, the hole that you're tracking becomes an absence of solid angle, and the complement on the sphere area is filled in. But then you turn around to walk back, and oh no, that absence hole gets bigger and bigger. And then if you cross through again, you cross through the amp loop path again, going the other way, you land right where you started, which is this patch of solid angle that's going to shrink, shrink, shrink as you go to infinity.
Okay.
So that would be linking number of 1 minus 1, right? It's like, hey, you kind of linked, then you unlinked. Still 0 overall. So no circulation in this case. And as we mentioned with the straight wire case, you're like, oh, you could really maneuver the current wire to get unlinked, right? Or get out of the maze, so to speak.
Yep.
Well, in this case, you could do the same thing, right? You could move that. You move the amp loop path, pull the wire. If you were willing to do that for an infinite amount of time, you could eventually get to the end of it and then pull the ring off or pull the loop off of the wire.
Yep.
All right. And now I can finally answer your question.
All right.
All right. So now that we've proven that Ampere's law is safe to use, we can use it in all cases because we've proven it for all cases. Notice that Ampere's law doesn't give you the B field value for any point in space. No. It merely gives circulation. Right. So Ampere's law just says B dot dP equals mu naught times the current that you encircle it by.
Yep.
And that current is signed. If going this way is positive, going that way is negative. So you need to have B field information to calculate circulation, don't you?
Yep.
As a matter of fact, you need to know the B field at every damn point on that path.
Yep.
In order to truly calculate it. But once you take the dot product and sum those things together, what comes out of this vector field information is just a number. So I want you to think about when you take this field information, this path information, and you calculate the circulation, you have taken an enormous amount of information, like multi-componented information, right? A bunch of 3 vectors, infinitely many 3 vectors across the path representing the field, the B field, and you've compressed all of that into a single scalar value. That is a lot of information loss.
Yeah.
That is a ton of information loss. And unfortunately, even though in our proof, we kind of finagled our way around needing to know the B field everywhere, didn't we? We finagled our way around needing to know what the path parameterization was or the wire parameterization. But because we finagled our way around that, we've got this law that really just applies to circulation. Right. And untangling it seems untenable because if you have so many vector inputs and it's only outputting a single scalar value, the operation itself has an immense null space. I know you took linear algebra, so I was hoping that this terminology would give it a little more tangibility. So the null space is of a Ampere's law integral. The null space would be every wire that didn't cause circulation net.
Okay.
Right. So if there was a wire way off in the distance that never passed through your amp loop, well, that wire contributed no circulation, did it?
Nope.
So that wire got sent to the null space, which is 0. Because when you map a bunch of things to a 0, like you could have had 4 or 5 different wires out in space that didn't interact with your amp loop. Those 4 or 5 wires all got mapped to 0. You cannot unmap them. You've destroyed that information permanently. It got mapped to 0. You can't unmap from 0.
You're like collapsing it down. You can't even see it anymore.
Yep, it's not. You can't unmix that paint. So therefore, Ampere's law can only unravel magnetic field information if sufficient symmetry exists to limit possible outcomes.
Interesting.
And an additional thing, it can only unravel magnetic field information from fields that weren't 0 circulation effects. So,
right.
only to find fields that caused net circulation, net non-zero circulation. So in other words, you can't use Ampere's law to figure out what the magnetic field caused by a wire that didn't interact with your amp loop was.
Mm-hmm.
That's gone forever. It's in the null space.
Yep.
If you did have some sort of a curved current wire that did pass through your amp loop, you may be able to, with sufficient symmetry, to unravel this and figure out what the B field would be that was caused by that one wire that interacted with your loop, but not all the other ones.
Really similar to Gauss's law.
Very, but there's a subtle difference that beat the crap out of both of our brains, and I think we're about to get through it.
All right.
So the null space, right, of Ampere's law includes any B field that contributed no circulation. So in other words, if you had three B field sources, B1, B2, B3, and you wanted to find the circulation caused by all three of them, thanks to linearity of integration in the dot product,
Mm-hmm.
you could do the circulation for each three and sum them together. But if sources 2 and 3 don't ever thread your loop, your amp loop, then their dot products equal 0.
Mm-hmm.
When multiple fields map to 0, you have no hope of finding those fields via Ampere's law. Perhaps if sufficient symmetry exists for source 1, we may be able to find B1. But the reason you need sufficient symmetry is because you just mapped a ton of vector information onto a scalar.
Mm-hmm.
So you're going to need a hell of a lot of information and constraints to unravel that. And then, yeah, let's talk a bit about Gauss's law, right? So in electric fields, the irreducible source element is the point charge. Once you prove Gauss's law for a point charge, Gauss's law is then valid for all charge configurations. Since any continuous charge distribution can be modeled as a collection of dq infinitesimal point charges.
Yep.
So my recommended homework for you would be prove Gauss's law for electric fields using polar spherical coordinates. Start with a point charge centered at the origin. This is all you need to prove general Gauss's law. You just need to prove it for a point charge, and I'm telling you that polar spherical coordinates will really help you do that with the flux calculation.
For starting with the point charge.
Yeah, because once you have the point charge, you're like, hey, that's it. Like, everything's made up of point charges. It's the
Right.
fundamental building block of electric fields. And the beauty of the point charge is you can put it at the center of your coordinate system, right?
That is nice.
Yeah, right. Like if the point charge didn't work that way, that'd be really rough because you'd have to do it for a point charge off to the side, right?
Uh-huh.
Or a point charge here or there. But no, because all you need to do is prove it for one point charge, and then you're golden.
All right.
But Gauss's law, similar to Ampere's law, has an immense null space as well.
Mm-hmm.
Any field, electric field caused by a charge outside of the Gaussian enclosed surface is a part of that null space. So Gauss's law can only tell you the electric field caused by a charge within the enclosed surface, and only with sufficient symmetry to limit the variables, right?
Mm-hmm.
In the same way, flux takes a ton of vector information over an entire surface and compresses it into a single scalar value.
Mm-hmm.
So to unravel it, you're going to need a lot of symmetry and additional constraints. But you have no hope of ever finding an electric field contributor that's not inside that surface because it's been sent to the null space. You'll have to use a different method. Gauss's law won't do. All right. So this is the breakthrough. As we've started to see in magnetic fields, the irreducible element is not the Biot-Savart infinitesimal current segment. Firstly, we talked about it in part 1. You can't just have a tiny little current segment floating in space by itself.
Right.
Right? Where's the current coming from? Where's the current going?
Mm-hmm.
It's physically impossible in isolation. And not only is it impossible in isolation, we're unable to prove Ampere's law with the Biot-Savart element alone. We had to integrate all of the little Biot-Savart elements to get a full closed loop wire.
Mm-hmm.
And therefore, the irreducible element in magnetostatics is the closed loop steady current wire. And that's where our brains were breaking.
Mm-hmm.
And we'll talk a little bit more about it here, but does that make sense where we like to think of sources as points because we love the electric field and it's easy to think about point sources, but in magnetism, it's just not that straightforward.
Right.
The irreducible element for magnetic fields is a closed loop steady current wire.
Yeah, because you can't have like a point. You can't have a point wired with current. That makes no sense.
No, not only that, but Gauss's law for magnetism proves it even further. Because Gauss's law for magnetism says that the flux through an enclosed surface is always 0.
Mm-hmm.
This means that there is no north pole separate from a south pole. There is no south pole of a magnet separate from a north pole. They come in pairs. You
Mm-hmm.
cannot have one without the other. And this lends itself perfectly to a current loop because a current loop is a magnetic dipole, right? You remember the magnetic dipoles, you run current in a loop,
Yep.
and then that will have a north pole and a south pole. That's essentially the start of a solenoid, right?
Mm-hmm.
A solenoid is just multiple of those stacked.
Right.
So the irreducible element is the wire loop. Now, what's interesting is in really advanced physics, like because when I was doing this, I was thinking, okay, let's say I have, I don't know, like a wire that maybe looks like this. So it gets thicker, it gets thinner, it kind of balloons out, right?
Sure.
So this is some wire with thickness. What I was thinking is, well, I can build this wire using a bunch of little current loop strands, right? There's one loop, here's another loop that I could build it with. In the same way that we can build a continuous charge distribution with a bunch of little DQs,
Mm-hmm.
you can build any current density, J, with a bunch of little strands of wire with current DI.
Okay.
And I thought that was pretty neat.
Yeah.
But then I looked into it more, and actually, in really advanced physics, they treat the current loops as if they're infinitesimally small.
Really?
Yeah, very similar to Stokes' theorem, where you start saying, okay, I stack these current loops on each other, right?
Mm-hmm.
And then they'll say, oh, well, the current from this one goes that way, the current from this one goes that
Right.
way. So they cancel on the inside
Mm-hmm.
and they only stay alive on the outside. Well, isn't that interesting and nifty? Because what does charge do when it's in a conductor?
Oh, it goes everywhere.
Does it?
They go to the outside.
It goes to the surface, right?
Yeah.
So when you run current through a wire, in reality, there's no current in the center of the wire.
Mm-hmm.
There's a bunch of maybe random free electron motion. Well, not even that. The free electrons are all at the surface
Right.
and they're flowing on the surface. So this is so convenient for that.
That's what this is saying. That's
Yeah.
really cool.
So, and this isn't what nature really is. Like nature isn't just a bunch of eddy currents of electrons and they, right? Like,
Mm-hmm.
but it's a beautiful model of nature that can be made to fit our purposes because in magnetostatics, the element is a closed loop wire.
Mm-hmm.
And so if you want maximum control, you don't want your wires to be really long. You want to make your wires really small, infinitesimally small and looped in. So I thought that was a cool connection. Also because Stokes' theorem is what takes Ampere's law on the integral scale and takes it down to the differential form.
Right.
So it's like there's a lot of similarities here. And like I said, this Gauss's law for magnetism, just more evidence that I think the current loop wire is the true irreducible element in magnetism. And with that, now we can actually answer your question. All right. Took 4 hours to get here, right? Better be good. Unfortunately, I didn't draw it yet. But your question was about an ideal solenoid. And in reality, and they'll never say this in the textbook, but to have a true ideal solenoid, you need two things. First thing you need is you need a cylinder that is infinitely long. So we've got this infinitely long cylinder. It goes to infinity on either end. Then the next thing you need is you need what's called a surface current. So think of this as a hollow cylindrical shell of conducting material.
Okay.
And you have this surface current that flows around it azimuthally. So I'll call that surface current. Surface current is very similar to current density. It's just a two-dimensional kind of sub-extension of it. So
Okay.
sometimes I'll call surface current K vector, but it's really related to J, or really related to current density. All right, so we've got this surface current that's traveling entirely azimuthally. That means that there's never any current going this way or that way.
Mm-hmm.
So right off the bat, are the solenoids we have in day-to-day life meeting the constraints here? Like that's an ideal solenoid. If I take a real solenoid, it looks like this, right? With the real solenoid, is there ever current traveling in the z direction?
Well, yeah.
Yeah, right? It's
Yeah.
looping around, so
Uh-huh.
it's mostly azimuthal. but it is the current is there is ultimately a component of current that goes in the z direction.
Mm-hmm.
So the real solenoid and the ideal solenoid are already different in that sense, right?
All right.
The other part about the ideal solenoid is we require infinite length, right?
Yep.
And no real solenoid has infinite length. Now you may be able to get the winding super, super, super tiny in radius with respect to the overall length. And that gets you closer to ideal. But I think the point is when you look at that Ampere's law proof in the textbook, they have a drawing of a real solenoid, don't they?
Yeah.
With the in and outs, right?
Yep.
The wires looping in and out. And that's just not the case. What they're deriving is the ideal solenoid. And for the ideal solenoid, you need the current to always be in the azimuthal direction, and you need the cylinder to be infinitely long.
Hmm.
So with that in mind, let's focus on how we calculate the magnetic field caused by an ideal solenoid, both in and outside the solenoid.
Feel cheated, kind of.
I know. I felt cheated too. All right. So we've got a few arguments we can use. Once again, right, with Ampere's law, you've got a bunch of vector information that you turn into a scalar,
Mm-hmm.
right? So we're going to need a lot of symmetry arguments here to make this work. And I'd like to start with the one that we discussed at the very beginning of the session, which was that there's only a single detectable axis that has a preferred coordinate system.
Yep.
And that's radius. All right, so there's the radial hat vector. Let's call this the theta hat vector. We'll call this the z hat vector. And that would be a coordinate, say, up here. But if I drew a coordinate, say, over here, then the r hat points in this direction. Z hat still has an absolute direction. And the theta hat would then be pointed like this. Okay, but like we discussed earlier, you have no way of telling where you are in the z direction or where you are in the theta direction, because if this tube is all there is that exists in space and it's infinitely long, you can walk to the left or right forever and it will always look the same. You can walk around the azimuthal direction, staying the same radius away, and this thing's perfectly cylindrically symmetric. So it'll look the same in all those locations.
Okay.
So because that's the case, we can immediately say that B, the vector field, can only be a function of R.
Understandable.
Yeah, and that's because if it was a function of z or phi, then we could use a field detector to orient ourselves in a way that's impossible to do.
Mm-hmm.
So in other words, but just because it's a function of R does not mean that it only has an R component. It could have a theta component that's a function of R. It could have a z component that's a function of R. We have reasons to believe that's not the case, but as of right now, symmetry itself only gets us this far. So I'm going to call it by undetectable change. I've been preferring to say that instead of symmetry because I feel like symmetry is such a loaded thing that we hear a lot.
Mm-hmm.
And it's usually just a hand wavy thing, right? In the solenoid derivation, they just say symmetry to shut us up. Stop asking questions. We don't want to answer them. All right. So now we've got to argue, for example, why the azimuthal field would be zero. So we would really like to show that this is zero.
Okay.
But we need a good argument for it. And I think the best argument for it is to do an Ampere's law in the r theta plane. Because, like, hey, we just proved Ampere's law. Like, generally, we ought to use it, right?
Let's do it.
So I'm going to take a plane in the r theta and cut a section out. And then we're going to do an amp path in that section and see why the azimuthal component of the field has to be zero.
All right.
Okay, so Ampere's law tells us that whatever path we choose, and let's go ahead and let's choose this path as our amp path. I'll use a different color for that. We've been using pink for amp. So let's use pink for amp. So we take an amp loop path in the r theta plane. And we ask ourselves, how much current is flowing through that amp loop?
Figure it out. All right.
What are you thinking with this loop that's in a kind of a section in the r theta plane? How much current is flowing in or out of that loop?
Hmm. Is it zero?
Why?
Because the current's not flowing that direction.
Exactly. The ideal solenoid, the current is all azimuthal, right?
Yeah.
So none of it's ever really passing through this loop. It's
Uh-huh.
actually perpendicular. The current is perpendicular to the normal of that loop. So we know that the right hand side has to be zero. And honestly, we should probably make this loop a rectangle to make our life a little easier. And you know what the heck? We like circles. We could do circles. Um, it can't be that hard. So if you were walking in this perfect circle, what direction would every step be in?
Um, in the theta hat direction.
Yeah, every step is in the theta hat direction. So in our theta hat displacement, so basically what we've shown is that dp is equal to r d theta theta hat because we're walking in a circle that's centered concentric with the origin of the or with the axis of the cylinder.
Yep.
So that's our displacement. So we know what our dp is, and therefore it's only going to be the theta component of b that matters, right?
Yep.
Basically, up here we could think of it as saying like br r hat plus b theta theta hat plus bz z hat, and then we're dotting it with dp. Well, dp, that step is all in the theta hat direction.
Yes.
And we know all that has to ultimately equal zero because there's no enclosed current, or there's
Mm-hmm.
no encircled current. Okay, so we do that dot product and we get b theta times r d theta must equal zero. So at minimum, either b theta must be zero, r must be zero, or d theta must be zero, right?
Mm-hmm.
Or I'm sorry, we're integrating this, aren't we?
Right. Yep.
Symmetry tells us that if b theta did exist, it would be constant, correct?
Mm-hmm.
Otherwise, we could detect where we were on the axis. R is certainly constant because we fixed that in our loop. We defined our loop that way, right?
Yep.
And we're doing 2 pi rotation, right?
Mm-hmm.
So if you sum up all the d thetas, all the little changes in angle, what are you going to get?
You should just get just one rotation, so 2
Yeah,
pi.
2 pi rotation, right?
Yeah.
All right, so which do you think is more likely to be zero? The theta component of the B field or 2 pi r?
Probably the theta component of the B
All
field.
right, right. This is not zero by definition. Like we made sure of it. We designed the loop, not zero. All right, so B theta's got to be zero. That is super helpful. So now we've gotten it down to B must be a function of R due to symmetry. We could still have a BR component that varies with R, but we do not have a B theta component. We sloughed that one. We were able to get rid of it.
Very
All right.
nice.
Oh, we were able to get rid of it for outside the loop or for outside the current wire, but you could probably see why inside would be the same argument, right?
Yeah.
Okay. So inside, outside, pretty much same argument.
Mm-hmm.
Now we have to destroy the BR component. Because remember, for the ideal solenoid, it's only got a Z field, right?
Mm-hmm.
So somehow we have to destroy this component. And we can actually do that using Gauss's law for magnetism.
All right.
And we don't even need to really do any math. We don't need to do any math because we've already decided that if there was an R component of the B field, its strength would only depend on R itself,
Mm-hmm.
not by Z, not by theta,
Mm-hmm.
right? So that means that if I had a BR component here, it would be the same as a BR component here. It would be the same as a BR component here. It'd be the same as a BR component here, or off to the side.
Yep.
They would all have the same length, right?
Yep.
Okay. So now I want you to imagine that I take a little volume element and I stick it there and I ask you, is the divergence going to be zero?
me think about this.
Because we know for the B field the divergence has got to be 0, right?
Yes.
You think the divergence
Wait,
will
hold
still
on.
be 0 if we
With
have an
the
R component there?
with the way you drew your shape, maybe not, because it looks like no. Well, hold on, because divergence tells you if we want it to be 0, the field lines have to enter and exit,
Right.
essentially.
Oh, I guess there is an entering and exiting thing going on, isn't there?
Yeah.
Oh, you know what we need to do? I'm sorry. I need to draw a better Gaussian surface. Sorry, that was bad.
No, you're good.
I think for that little element, you're right. I think it could work out. But I think that if I drew an honest to goodness Gaussian enclosed surface like this, so let's say that's my Gaussian enclosed surface. And divergence is positive when?
Oh boy, divergence is positive when you have more field lines exiting than you do entering.
Correct. Do we have Well, okay, we also agree that the Z component of the B field has to be dependent on R, right?
Yes.
Like the Z component can't change according to Z, can it?
No, of course not.
Like due to symmetry, we're confident that a BZ here would be identical to a BZ here.
I just got a notification. I'm sorry to pause. I just got a
Yeah.
notification that my computer was going to restart in 10 minutes. I tried
Oh,
to say no, but
so
if
did
it
mine,
does,
yeah.
okay.
Okay. Thanks for letting me know. Mine actually had the same thing.
Okay.
We'll know if we crash. We're
All
almost
right.
there. But because of symmetry, we can't use field information to know where we are in the Z coordinate system
hmm
because it's perfectly symmetric in that direction. So BZ here and BZ here would have to be identical, right?
Right.
So any negative divergence from a field line entering on the right side
hmm
would immediately be canceled out by positive divergence from a field line exiting on the left side.
hmm
So the BZs aren't going to help us solve this problem. The BRs is all that's left. Are there any BRs that enter the Gaussian surface?
No.
No, they would all have to either exit or enter, right?
Yeah.
So therefore, for there to be an R component of the B field that only varies with R because of symmetry,
hmm
if there was a non-zero BR, that would directly violate Gauss's law for magnetism.
Okay.
So with that, we can say BR as a function of R has to be 0 to obey zero magnetic flux. Or zero magnetic flux. Through an enclosed surface. We're so close. Those are the harder two arguments, but we've killed off the R component, we've killed off the theta component, right?
Right.
So all we have left is B vector as a function of R could have a Z component that's dependent on R. And that's it. So with that, I'm going to clear off a lot of space here. Actually, no, I can clear this whole thing at once. There we go. All right. Oh, whoops. I shouldn't have erased that. We just have to draw our ideal solenoid again. It goes to infinity in either direction. And it looks something like this. And we know at this point, by symmetry and a lot of other stuff, that the only possible component of B field the ideal solenoid could have is a Z component.
Yep.
And it can only be dependent on R. It can't be dependent on theta or Z.
Nope.
So now we can use Ampere's law to wrap this up. Because, hey, we proved it. May as well use it.
Let's do it.
All right. So I'm going to cut an Ampere. Well, actually, you know what? Let's do it on the outside. Okay, I'm going to draw an amp loop right here. My Wakeham's starting to bug out. All right. So if you have an amp loop here, ostensibly there could be a B field right here, right? There could be a BZ there. And there could be a BZ up here, right? Is there going to be any component of the B field in this direction?
Sorry, draw that again.
Will there be? Yeah, it's a bad color, isn't it? Let's use a lighter blue. So there could be a BZ here, right? As a function of R. There could be a BZ up here.
Yep.
As a function of R. We would probably expect it to get weaker as it got further away, huh?
Yeah.
But is there any component of B that would point in the direction of this path or this path?
No, of course not. We just
No.
proved that.
Right. We killed the radial parts.
Uh-huh.
So now we run Ampere's law for this loop and we say B dot dP equals mu naught times I encircled. How much current are we encircling?
Well, the current is going, kind of like for
Yeah.
our ideal solenoid, it's going that direction. Can it be that the current could flow through that amp loop?
Well, but is the amp loop touching this cylinder shell?
It's not, so it can't.
So it can't have any current going through it. So we
No.
know the left or the right hand side must equal 0. Then the left hand side could be broken into a series of walks. We could walk from there to there, right?
Mm-hmm.
How much circulation would that give us?
None, right?
None. There's no field in that direction, right?
Yeah.
Then we could walk in this direction. How much circulation would that walk give us?
There's some thief there.
And we give this a length. We'll just maybe call it L.
It'll give you some positive circulation there because you're walking with the B field.
Yeah. And what would that be equal to?
It would be BZ dot. So it would be, you got an integral still. BZ.
Yep. But we know that BZ is constant that whole walk because it's
Yep.
only dependent on radius.
So BZ dP cosine of 0 degrees, I guess.
Yeah. Cosine 0 is 1, and then dP, you can pull out BZ because it's constant for any given radius.
Yep. Mm-hmm.
And then you just get BZ times L. Then you can walk down this side, and once again, that's going to give no circulation,
Mm-hmm.
no B field in that direction. We showed that. Now we're walking against BZ, aren't we?
Yeah, negative.
So it'd be negative BZ of, oh, I should have done something a little different here. I should have called this maybe BZ of R and then BZ of R plus DR. Because it's a different radius we're at, isn't it?
Yeah, it is.
So I'll maybe do BZ of R plus delta R up here. So I'll go fill that in a little different.
That's a good point.
Yep. And then minus BZ of just R times L, right?
Mm-hmm.
This has to equal 0. Length is the same, right?
Mm-hmm.
So somehow BZ evaluated at a different R, right?
Mm-hmm.
Minus BZ evaluated at a different R have to cancel and give you 0. Because L is the same for both, right?
Yeah.
So what's the only way that's true?
If BZ of R plus delta R equals BZ of R.
Right. Which would mean that BZ doesn't change with radius, right?
Yeah.
So BZ must be constant. Must be constant outside the solenoid. Boy, this Wacom bug's really slowing me down. I hate it. After like an hour and a half, it always does this.
Do you need to exit the Zoom meeting?
Shoot, we're so dang close. Well, we'll see, but I think we're good. So BZ, I'm gonna call this BZ out, maybe. They're dealing with the outside there.
Mm-hmm.
Now it must be constant. Now this is kind of a wacky part of the argument. If it must be constant, whether it's here or here or here or infinitely far away, what's the most likely value?
It's 0.
Right, because if you go infinitely far away from the wires perpendicular, at some point the field has to decay to 0, right?
Yeah. Uh-huh.
So because the field must decay to 0 at some point, and we've shown that BZ is constant on the outside, that's where we can go ahead and say
BZ outside is 0.
0. Yeah, and in truth, because Z is the only component of B, we can now say that B out is simply 0.
Right on.
So that's
part
of the argument.
Yep.
Now we have to make a similar argument on the inside. So on the inside, we could cut something like this, right? And this is like, we're finally getting to the step that the book starts with.
Yeah.
So now our amp loop looks like that. And we'll give it a length here. And we know that those sides aren't going to provide any circulation, are they?
No, of course not.
So the sides don't provide circulation. the outside doesn't provide any circulation, right?
Mm-hmm.
Its field is zero. So the
Mm-hmm.
only part that's going to provide circulation is there's going to be a BZ component here.
Yep.
Maybe call it BZN. And once we figure that out, that's just okay. BZN times L is the circulation, right?
Mm-hmm.
If we're walking that way. So maybe we start here, we walk from there to there. Then we walk from here to there. That's no circulation. We walk from here to there, no circulation.
Mm-hmm.
And we walk back and we've done the full amp loop, and this is all the circulation there is. How much charge, or I'm sorry, how much current is enclosed now? We finally have some current going through
Yeah,
it, right?
there's some current there.
Let's say, let's say that the surface current K is maybe defined as a current per unit length. So I'll call it current per unit length. Maybe something like that. Or maybe better. Oh, what? I'm trying to remember exactly how they do it in the text. Don't they say like, oh, that's right. They say they have this number called little n.
Yep.
And little n is the number of loops divided by the length, right? Total
Mm-hmm.
number of loops divided by the length.
Number density.
We could probably say that surface, like that the amount of current passing through a spot is maybe like surface current times length. What the heck? I'm just going to start calling the current I. So I'm just going to say like I times length. So to find the total amount of current passing through here, if the surface current is like current per length or something like that, wouldn't we need to times it by length to get it out, to get it to current as is? Boy, I didn't expect this to be the spot that really tripped us up. Because now there's not a finite number of counting, right? We've got an infinite spread. I'm going to call K the current divided by the length. So this is like total current divided by the total length, but the total length's infinite.
Mm-hmm.
Shoot. Well, I suppose at this point, maybe the best thing we could do is just pretend that we have a bunch of concentric circles that flow like this, and they truly go in an azimuthal direction and loop in on themselves, right?
Mm-hmm.
And we could say that there's like n of those. So number per unit length equals little n. And then we could say that the total amount of current there would just be the current in a single strand, which we could just call I, because that's what they're going to do with the non-ideal solenoid, right?
Yep.
And so it would just be, hey, we have the number of loops sub little n times the length we have, right?
Mm-hmm.
And yeah, I should have called that big N over big L. But now we've got this smaller length that we're having current flow through. So it'd be N times L would give us the number of loops that pass through the loop. Right? Let's see here. So this would be, I wish I could write faster. The number of pass-throughs, you could call it, maybe. I don't know.
Right.
And please, I know this is getting unclear and the board's getting very messy and the writing is so slow. Hard to think when the computer is slow.
Right.
So number of pass-throughs would be the number density of the coils
Mm-hmm.
times the length that you've covered with your amp loop, right?
Yep.
Then we would simply times that by I, the current through each of the loops. To get that, then we need the mu sub naught, because that's a part of it too. That's a part of Amp's law. And then, hey, we just divide the L over the length of our amp loop, and we would get BZN equals mu naught times lowercase n, or the number density of turns,
Mm-hmm.
times current in each turn I. And that is the equation for the B field inside of an ideal solenoid.
Yep, I remember.
So we finally got there. I know that was a long way to go, but I think the point is, I think where you and I were getting confused when we were like, hey, with Gauss's law, we need to do a Gaussian surface for every charge, you know, charge
Mm-hmm.
distribution that we're trying to figure out contributes to the E field. Don't we have to slice up the solenoid into a bunch of sections of small little current segments
Mm-hmm.
to find out how much those contribute? However,
Yeah.
what I'm saying is that the ideal solenoid is just a single wire loop, and that magnetostatics, the irreducible element, is a single wire loop.
Right.
So because it's all one wire, you can
Mm-hmm.
just do one amp loop. It
Mm-hmm.
interacts with the amp loop. It's going to pop out the absolute B field once you have these symmetry conditions and arguments in place. I should have drawn this out beforehand, but I ran low on time.
No, you're good. That was perfect. Wow, that was amazing.
Well, what do you think? Question answered?
I think so. That's a really good way to think about it.
Cool.
Oh, it's just one wire, so you don't need to
Yeah,
break it up into infinitesimal
exactly.
DL or
Just like
D.
with one charge. Yeah, with
Yeah.
one charge in the E field.
I
Well,
love how it
cool.
all comes through,
Yeah.
connects at the end. Good job. Wow. So,
Well,
okay, I have a question for you.
yeah, please.
How does this compare to the Faraday's law endeavor that you had to go through?
Ooh, way harder.
This one was harder?
Oh yeah. This has been months in the making. Um, I'm very proud of it. I
Should be.
think I potentially have the most could explain to a fifth grader visual proof of general Ampere's law that I've ever seen. Um, I've looked online, I've looked on YouTube, I've looked all over the place. Everywhere else uses complicated lemmas or topology language that not the average person knows what the hell
Mm-hmm.
means. So I think I found a nice middle ground for the Ampere's law proof, and I learned a lot more about it through that question. I've never felt more confident in what it does,
Mm-hmm.
right? What it really does, because sometimes the way they teach it in class, they use these laws to find things like the B field or the
Mm-hmm.
E field. And so you start to associate it with, oh, Ampere's law tells us the B field.
Right.
Gauss's law tells us the E field. It's like, no, Gauss's law tells you the flux. Ampere's law tells you the circulation with sufficient symmetry. And if those elements were engaging with your loop or your enclosed surface, then you can maybe unravel it and
Mm-hmm.
figure out what the field is. But we can't even say, like, even in our case, we said the B field is mu naught Ni.
Mm-hmm.
Well, that's true if that solenoid's the only thing in the world, right? There could be another wire loop over here, and Ampere's law doesn't tell us
Yep.
about that one. We would have to go and do Ampere's law for that element and hopefully unravel the B field and then sum the two using superposition, right? So I think it's really neat. I think my next step is to revisit Faraday's because I've done it with Gauss's. That's kind of what I told you I thought would be great homework
Mm-hmm.
is trying to do it for Gauss's. So I've done it for Gauss's. I've done it for Ampere's. Faraday's law I've had a lot of thoughts about, but I think there's a lot of in-depth exploration that could happen there next. Unfortunately, I do know that in that exploration, I'm going to have to dig into relativity because one of the answers to that is one of the reasons Einstein wrote his papers was because of Faraday's law and some
Okay.
confusions around it. So
Interesting.
that's kind of what comes next.